Here I will explain about the well-ordering principle of natural number. That is, in natural number, if you take any set, let's say A, which is not empty, then A has a smallest element. At this point, I may assume that reader have some familiarity about the definition of groups and subgroups. Okay, so this is fairly easy for those who have some at least some familiarity about group, subgroup, and this is a very nice example. And one should start from here, simple structures, right? So what is Z? Z is 0 plus or minus 1 plus or minus 2. As I said, they look like this. Okay, and see the term which I use, the term that look like, it's a like slightly rough term. It's used for in to say, to represent something. Okay, I will use this term again and again. So this is Z, and I like to see what are the subgroups of Z. Okay, we know that Z with respect to addition is abelian group. Okay, and I wanted to see that what is going to happen. I mean, what are the subgroups? Okay, for Z. Let us see that. Okay, so what is a subgroup thing? I have to start from a subgroup. I mean, in abstractly, I will try to classify how do they look like exactly. Okay, this is the thing, and subgroup should be non-empty, and zero should be there in the subgroup because of that is identity. It's non-empty and zero should be there, and there may be many more elements. My claim is very simple. All subgroups looks like NZ where n belongs to natural number union 0. That is, they look like sums for some. They look like 0 plus or minus n plus or minus 2n plus or minus 3n and so on. This is what my claim 80 is, and let's prove that. First of all, what I'm going to do, take Z case 1, take H. Suppose H is 0, then I'm done. This is 0 into Z, right? Just 0, right? So I'm done. The interesting case is where it is non-trivial. Suppose H is not only 0, something more than that, okay? It is non-trivial. Now take A to be H intersection natural number. Okay? First of all, this is not empty. Why? I will explain orally why. Suppose there is an element X belongs to H and not equal to 0. Of course, I said there is something more than 0 and not equal to 0. Either X belongs to natural number or minus X belongs to natural number, right? So X is this thing, minus X. X and minus X both are there in H because H is a subgroup. Either X in the natural number or another thing. So this is non-empty. Minus X, okay? This is non-empty. And this says that let n to be the minimum. This is a key factor. N to be the minimum of H intersection. That is A. I already said that A. So clearly, n belongs to H. That's not a problem. So that implies n plus n belongs to H. 2n, that is 2n. 3n minus of those things belongs to H. So this says that nz contained in H. So the claim is reverse. Let an abstract element small a belongs to H. Okay? Small a belongs to H. Then by division algorithm, basic number theory says the division algorithm, remember that n greater than 0. N greater than 0. Here I had intersect with natural number. Natural number start from 1. N greater than 0. Okay. Remember that. I'm not intersecting with the whole numbers. So then I can divide by n. I will get quotient plus remainder. With the remainder condition, it can be 0 or R should be strictly less than n, greater than 0. This is a condition for reminder for any n. Okay. Cation can be positive, negative, doesn't matter, but n should be like this. Okay. Now, what I'm going to do, you see that a minus nq, that is what R. A is inside H, nq. N is inside H, so nq inside H. That implies R inside H. And this is impossible. R should be 0. Otherwise, R greater than 0, less than n, contradiction to the fact. To the fact, okay, to the fact that n is minimum of q. See, otherwise R should be the minimum. R is greater than 0 means it's a natural number, right? And R is less than n, it should be minimum. Because R is in here, it's a natural number. It's contradicts to the fact to the minimum of this. A. So that says that clearly R is 0, that implies A is nq. And A looks like n into something. So A belongs to nz. And this is arbitrary. This implies H is also subset of nz. That says that H equal to nz. And how to choose the n, you know that, right? Using the minimum. So the conclusion is any subgroup, okay, any subgroup of Z, any subgroup looks like, should put code nz, where n belongs to natural number union 0 for some n, okay? For some n. So this is the classification. Finally, the subgroups of Z is equal to nz such that n belongs to natural number union 0. A union 0 is very important. This is how we classify the subgroup of Z. Okay. So we will continue this and we will understand the quotient groups and we will name them and let's see. Thank you.